Welcome to the fourth lecture on circles. So, in the last lecture we had discussed the relation between a line and a circle. We had also seen how to calculate the intercept made by a circle on both the x and the y axis. So, in this lecture we are going to take a few problems on how to find the intercepts made by a circle on the axis and also the intercept made by a circle on any arbitrary straight line. And after that we will start a new subtopic where we will derive the equation of tangent and normal to a circle at a given point, and that will be followed by the definition of the power of a point with respect to a circle. So, let us take this problem here. It is said that so we have to find the equation of a circle which touches the x axis at a distance of 3 units from the origin, and further the circle has an intercept on the y axis of length 2 times square root of 7. So, let the x square plus y square plus 2 g x plus 2 f I plus c equal to 0 be the general equation of the circle, and it is said that the circle touches the x axis at a distance of 3 units from the origin. So, it is mentioned that the circle touches the x axis. So, by touches we mean that if this is the origin, this is the x and this is the y axis, what we mean to say is that the circle touches the x axis at a point which is 3 units from the origin. So, one situation is where the circle touches. So, this is the circle and it touches the x axis at exactly one point which is 3 comma 0. So, this is one possible case. So, what this basically implies is that if we take this case of 3 comma 0, the other case could be that the circle touches the x axis at this other point minus 3 comma 0, which is also on the x axis and which is also at a distance of 3 units from the origin here, since this and this are both 3. So, if we, for example, if we take this case, then the only point which lies both on the circle and the x axis is 3 comma 0. Now, let us see what are those points on the x axis which can also lie on this circle. So, we can generally denote a point on the x axis by these coordinates. The y coordinate is 0, and let us see which are these points of this type, or for what values of a will such a point lie on this circle. So, that basically means is that this equation has to be satisfied with x equal to a, y equal to 0. So, what we get is this equation, and since the circle touches the x axis at exactly one point, it means that although this quadratic equation has 2 roots. So, in general there are basically 2 different values of a which will satisfy this equation, but then and those 2 values will basically correspond to 2 different points on the x axis which will lie on this circle. But in this problem, since we know that the circle touches the x axis at exactly one point, it is implied that both the roots of this equation must be equal to 3, and that is only possible if the discriminant of this quadratic equation is 0, which implies that g square is equal to c. Further, since a equal to 3 is the root of this equation, this should be satisfied with when we put a equal to 3 here. So, then if we put a equal to 3, we get 9 plus 6 g plus c equals 0, but c is g square. So, that is the same as writing 9 plus 6 g plus g square equals 0, and this is nothing but, so this is the left hand side is g plus 3 whole square equal to 0. That implies that g is equal to minus 3, and therefore, since c is g square, c is equal to 9. It is also said that the intercept of the same circle on the y axis is of length 2 times root 7 units. Now, in the previous lecture we have already seen that the length of the intercept of a circle on the y axis is given by this equation, which is equal to 2 into square root of f square minus 9, because we have just seen that c is equal to 9 in the previous slide, and this is given to be 2 times root 7. And from here it follows that f is equal to plus minus 4. So, essentially we get 2 different circles if we consider the case where the circle touches the x axis at this point 3 0, and that is very natural also. So, the first circle C1 corresponds to value of g, which was minus 3, let us say f equal to minus 4. So, the center of the circle minus g minus f is equal to 3 comma 4, which is this point, and the if you draw the circle, it is going to be something like this. So, this is the circle C1, and if we take the, instead of taking f equal to minus 4, if we take f equal to plus 4, then we get the other solution. If we take f equal to plus 4, we get the center minus g minus f as 3 minus 4, and that is this and that is this circle in red. And similarly, if we had started, instead of starting with 3 0 as the point on the x axis which touches the circle, if we had started with minus 3 comma 0, then we will again get two circles which are, one would be here and the other would be like this. So, totally there will be 4 circles, 4 possible circles which are going to satisfy these two conditions in the question. So, I will draw the other two circles over here also. And the other one will be so these two are the other two circles which touch the x axis at a distance of 3 units from the origin, and whose intercept on the y axis is 2 times root 7. So, we did not show the intercept, but that should not be very difficult. We just have to extend this y axis upwards, and then we will see that if we draw this circle C1 completely, it will be something like this, and this C1 is going to intersect the y axis at 2 points, and this length you can check will be equal to 2 times square root of 7, and the intercepts of the other 3 circles will also be the same. In the last lecture, we had derived the formula for finding the intercept made by a circle on both the axes. But what if we are asked the following question? So, we are given a circle and we are also given a straight line, and we are asked to find this length, which is the, so this length is called the intercept made by this circle on this straight line. So, we had not derived any general formula like that, but it is not very difficult to do so, and this is what we will illustrate through this next problem. So, let us take another problem. L1 is a straight line passing through the origin, and L2 is this straight line x plus y equals 1. Further, it is said that the intercepts made by this circle is the same on both the straight lines. It is of the same length. So, the lengths are, the lengths L1 lengths of the intercepts are equal. Then it is asked, because the equation of the first line L1 is not given. So, it is asked as to which of these 4 equations could possibly be the equation of L1. So, let us first find the value of the intercept. So, we have this circle, and we have a straight line L2 whose equation is x plus y equal to 1. So, it is something like, if we were to draw, then let this be the origin, and clearly this straight line is the one which I have drawn in blue, and the circle, if we see, it has a center at x equal to half and y equal to minus 3 by 2. And the radius of the circle is so, as we can also see, this circle passes through the origin. So, essentially this distance, which is square root of 5 by 2, is going to be the radius of this circle. So, I have drawn it approximately. So, and as we can see, this circle intersects the straight line L2 at 2 points, and this is the length of the intercept made by this circle on this line L2. So, now the question is, how do we find this length? So, obviously, the simple method is to find both these points of intersection. Now, any point on this straight line is going to satisfy this. So, suppose if we have a point x comma y, then this x and y has to satisfy this equation, because this point is on this straight line. So, in general, so from here we see that y is equal to 1 minus x. So, any general point on the straight line will be given by the coordinates x, and x coordinate is x and y coordinate is 1 minus x. So, if we add both the coordinates, we will get 1. So, all points of this type are basically on this straight line. And then we are looking for such type of points which also lie on the circle, because we are interested in finding these points of intersection. So, the points of intersection will be those points which are also on the, which are both on the straight line as well as on the circle, and therefore, any such point which is on the straight line and which is also on the circle must satisfy this equation with y equal to 1 minus x. So, if we write down that equation, we get x square plus 1 minus x whole square minus x plus 3 into 1 minus x equals 0, and if we simplify this, we get x square minus 3x plus 2 equal to 0, which implies that either x is 1 or 2, and that basically corresponds to the 2 points of intersection. So, when x is 1, the y coordinate will be 0. So, one of the points of intersection will be 1 comma 0, So, that corresponds to taking x equal to 1. So, that we have got by solving this quadratic equation, and the other possible value of x is 2, but then the point will be 2 and 1 minus 2. So, the coordinate of the other point of intersection will be 2 and minus 1. So, now that we have both the points of intersection, the length of this intercept is very easily seen to be square root of 2. And then coming to the second part of the question, it says that there is another straight line L1 which passes through the origin. So, there is another straight line which passes through the origin. So, it could be something like this. So, this is the other straight line L1 which passes through the origin, and it is said that this straight line also makes an intercept on the circle, and the length of the intercept should be the same as the length of the intercept made by L2, which is square root of 2. Since this line passes through the origin, the general equation of this line will be y equal to mx, where m is the slope of this line. And then, as we did for the line L2, we will also have to find the points of intersection of this line with the circle, where a job is made a little easy because we already know that the origin is one of the points of intersection, because both the straight line and the circle pass through the origin. And then let us try to see what the coordinates of the second point of intersection is. So, any point on this straight line will be of the type x comma mx, because the y coordinate is m times the x coordinate, and for any such point to be also on this circle, the equation of the circle must be satisfied with y equal to mx. That is, if we put y equal to mx, we get this equation. So, there are two values of x which satisfy this quadratic equation, and those two values will basically correspond to the 2 points of intersection. So, the two roots are x equal to 0 and x equal to 1 minus 3m by 1 plus m square. So, the solution x equal to 0 corresponds to the point 0 comma 0, the intersection point of intersection 0 comma 0, and x equal to 1 minus 3m over 1 plus m square corresponds to this other point of intersection, whose coordinates will be so now we got the coordinates of both the points of intersection. Therefore, L1 which is y equal to mx intersects the circle at the origin and this other point and therefore the length of the intercept will be the length of the intercept made by the line L1 on the circle C is going to be the distance between these 2 points, and this should be equal to the intercept made by the line L2 on C, which is square root of 2, and hence we have the equation which is square root of 2 should be equal to the distance between these 2 points, which will be on simplifying this we get so there are actually 2 different values of m. The intercept of L1 will be square root of 2. So, from here m is either 1 or minus 1 by 7. So, L1 could be, the equation of L1 could be y equal to x, or so both these straight lines will have the same intercept of square root of 2 on the circle. So, if we see from all possible choices, then we see that choice B corresponds to this y equal to x, choice B corresponds to the straight line y equal to x, which is one of the possibilities that we found, and also choice C corresponds to the other possibility that we found. So, next let us derive equation of the tangent to a circle at a given point. So, suppose we have this circle and we would like to find the equation of the tangent to the circle at a point having coordinates x1, y1. So, we have this circle here, the center as minus g minus f, and we have a point P which is on the circle having coordinates x1, y1, and we would like to find the equation of the straight line, which is the tangent to the circle at this point P. So, this is the tangent, and we want to derive the equation of this tangent. Now, suppose we have a point x y on this tangent, then the slope of the tangent is y minus y1 divided by x minus x1. The slope of the line joining this point P to the center of the circle, so the slope of this line is y1 minus f divided by x1 minus g, which is equal to y1 plus f divided by x1 plus g. So, this is the slope of the line, this is slope of OP. Now, we know that the tangent at any point P on the circle makes 90 degrees with the line segment joining that point P to the center of the circle. So, essentially this line OP and the tangent are perpendicular to each other, and therefore, the product of the slopes of this line OP, line segment OP, and the tangent should be minus 1. So, the slope of the tangent times the slope of the line OP is minus 1, which implies that and a little bit of simplification gives us but since the point P lies on the circle C, the coordinates of this point P must also satisfy the equation of the circle, and therefore this must be true. Or so essentially we can replace this right hand side in the equation of the tangent by this quantity, and therefore we get the equation of the tangent to be which can be simplified to so this is the equation of the tangent to a circle having the general equation x square plus y square plus 2gx plus 2fy plus c equals 0 at the point P, which is x1 y1. So, just as we had derived the equation of tangent to a circle at a given point P, we next derive the equation of the normal to a given circle at a point on the circle. So, suppose we have this circle where this is the center and we have a point P on the circumference. So, the normal is given by the line joining the center to this point P, which is this line. So, now the objective is that if we are given the equation of the circle and if we are given the coordinates of this point P, which is on the circumference of the circle, then the objective is to find the equation of this normal. So, suppose that the equation of the circle is this, with the center at minus g minus f, and suppose there is a point P having coordinates x2 y2, which is on the circumference of the circle. Then our objective is to find the equation of this normal line, or equation of the, then our objective is to find the equation of the normal to the circle at the given point P. Now, it is clear that the slope of the normal, the slope of the normal at P equals y2 minus f divided by x2 minus g. Now, we have another point if we have any general point on this normal, say x y, then the slope, or so suppose we have this point, this is any general point on this normal line, then this slope must also be equal to the slope of the line segment between any point on the normal line and the center of the circle. So, this slope of the line between the center and the point P must be the same as the slope of the line between any point on this normal line, let us say Q, and the center of the circle, because essentially both these lines are the same line, they are basically the normal. Therefore, this must be equal to the slope of the line segment OQ which is equal to y minus f over x minus g. And if we simplify it further, we get which implies that is so this is the equation of the normal to the circle at that point P. Next, we derive the length of the tangent to a given circle from a given point. So, let us say we have a circle here whose equation is this. And this is the center of the circle. And suppose we are given a point P having coordinates x 1, y 1, and then we are asked to find the length of this tangent P t. So, this length P t, where P t is a tangent to this circle at this point T. So, clearly this is 90 degrees, and we are asked to find this point, we are asked to find this length. We know that this length O t is the radius of the given circle, which is g square plus, which is square root of g square plus f square minus c. And this distance can also be calculated. It is given by OP is square root of this expression, which is square root of x1 plus g whole square plus y1 plus f whole square. We realize that OPT is a right angle triangle, and therefore, from the Pythagoras theorem we know that OP square is OT square plus PT square, that is PT equals square root of OP square minus OT square, which is, so OP square can be found from this equation. So, OP square will be x1 plus g whole square plus y1 plus f whole square, and OT square is the square of the radius, which is g square plus f square minus c. So, at the end this is the expression of the length of the tangent PT from a given point P to this circle, whose equation is this. So, essentially here we will be usually given the circle of the equation of this circle will be given to us. So, these coefficients g, f and c will be known. Similarly, the coordinates of this point P will be given to us, they will also be known, and then we will be asked to find this length, the length of this tangent. So, we can readily use this formula where all these, so these x1 and y1 is known and g, f and c are also known. in the next lecture we will define what is meant by the power of a point with respect to a circle, and we will also discuss some problems, solve some problems related to tangent to a circle at a given point and also normal to a circle at a given point on the circle. Thank you.